Today we are going to learn about the VSEPR theory and what that stands for and how that relates to the 3D shape of molecules. Now this is three-dimensional. And if we can determine the shape of the molecule, that will help us determine polarity, which in the long run will help us determine the properties of these molecules. Properties such as melting point, boiling point, viscosity, different types of properties and how they react is determined by their molecular shape and polarity. And to determine polarity, we first have to learn what shape they're in. So this is called the shape sheet, and this sheet is on Google Classroom. It's under your toolkit. This is something that you can use for a test, quiz, or final exam. So if you have a printer, I would highly recommend you print it out so you have this to use. The columns are nice, and more importantly, this column right here is going to be all the shapes. We really only are going to be using the top 5 boxes. We don't really get into these ones down here for our class. So looking at page 2 in your notes, this is a review of Lewis dot structures. This is looking at the periodic table, and from that on the periodic table determining how many valence electrons they have and how many they need to share in order to become stable. So to determine the valence electrons, you draw the dots around it. Group 1 has 1 valence electron. Group 2 on the periodic table has 2, 13, 3, 14, 4, 15, 5, and so on. Max number you can have is 8. The alone pairs, remember those will become the shared pairs. And we're going to go over a few examples here. Redraw according to the shared pairs. Non-bonding pairs should be drawn outside the atom, etc. You don't have to circle the atoms, but remember that most of the elements want to have 8 valence electrons. Boron and aluminum are special. They only need to be 6 to be stable. And hydrogen only needs to have 2 to look like helium. Remember, these dots represent the valence electrons. Those are the outermost electrons that determine the behavior. Bromine is a group 17 element, so therefore bromine will have 7 valence electrons, with one of them being alone. I'm going to leave that one alone electron right here on the other side because I know that's going to be called a shared pair. 1, 2, 3, 4, 5, 6, 7. And Br2 is formed. There should be nothing new there. Both bromines now have 8. That's why bromine is a diatomic molecule. It is more stable as a pair than being alone. Silicon tetrachloride. Silicon's going to be in the middle. It's group 14, so silicon has 4 valence electrons. Chlorine each has 7. So out of the 7, only 1 are alone. So the 4 chlorine are going to come and bond to these lone silicon atoms. Optional if you want to put all the dots around all the chlorines. I wouldn't mark something like that wrong. It gets a little tedious, but there they are. So it's silicon tetrachloride. Silicon dioxide. Silicon still has 4 valence electrons and all of them are alone. Each oxygen has 6 valence electrons. And out of the 6, 2 of them are alone. So what happens there, kind of hard to do in pen because I can't erase it. But we have shared pair, and these will form a double bond there. We're going to use one here and one here, and it forms a double bond on both sides. Those are little arrows that I'm drawing there. So silicon dioxide forms double bonds on both sides. So, yes, these are all Lewis structures. These are all drawn correctly, but they're not drawn to the correct shape. So we are going to take what we already know about drawing Lewis structures, and now we are going to use the shape sheet or the VSEPR model to determine the shape of these. VSEPR stands for valence shell electron pair repulsion. That's what it stands for. You're going to want to know that for any test, quiz, final exam. and it just in the name, a valence shell electron pair repel. Well, electrons have like charges, so that makes sense that they repel. And when they repel, they change the shape of the molecule. They bend everything downward. Okay? So, for example, CH4, how do I know that's tetrahedral? Well, I started with carbon, group 14, and then my 4 hydrogens come in. Should have left myself more room, but I didn't. Now, if you were to draw this on the Chapter 6 test, I would mark that incorrect because that is not the actual shape of CH4 methane gas. You have to use your shape sheet to determine the actual shape. And the actual shape here is tetrahedral. We have carbon, and there is 4 hydrogens bonded to it. Okay, this one has 3. That's not going to match. This one has 3 molecules, and then there is a lone pair on the central atom. The central atom is the one in the middle. So in this case, the carbon's in the middle, and these are your 4 hydrogens. So this is actually a 3-dimensional shape. So to draw that on your test, in order to get it correct, you would have to draw it in the tetrahedral shape, which is like this, which we drew the tetrahedral shape when we drew the diamond structures. So it's kind of like a 3D pyramid there if you actually look at it in 3D. What is the shape for pH3? Remember, phosphorus is a group 15 element, so it has 5 valence electrons. 3 of them are lone, and the hydrogens are going to come and bond to those as such. So to figure out the shape, we go to the shape sheet and we say, okay, our phosphorus, in this case, our central atom, has 1, 2, 3 pairs that are considered what we call bonding pairs, and there is 1 lone pair. And this whole valence shell electron pair repulsion, these lone electrons don't want to be by one another. So they draw a big old balloon around them because even though they're small, they push everything else in the molecule down. Everything gets strained and gets pushed down. So the actual shape is going to be this one right here, where we have phosphorus in the middle, we have our 3 hydrogens, and this balloon thing here are lone pairs. So you can see right here in the bent shape, we have 2 lone pairs. And then we would name it trigonal pyramidal. So we would just go ahead. So the shape of pH3 would be trigonal pyramidal. So if you want to get that right on your test, if you want, that was terrible. If you want to draw that correctly, we're going to have to torque those hydrogens down because these lone pair of electrons, this valence shell pair of electrons, repel each other and they push everything else down. Sorry, I look at the camera screen once in a while. You should be able to recognize non-bonding pairs. These are non-bonding pairs, non-bonding pairs. There is 0 non-bonding pairs on on the carbon CH4 there. Bonding pairs are pairs of electrons that bond carbon and hydrogen. There is 4 bonding pairs. On this one, there is 3 bonding pairs and 1 non-bonding pair. Those would be test quiz type questions. Right now, what I would like you to do is go ahead and stop the video and see if you can do CF4 and BCl3. I will give you a hint. Remember, boron only needs 6 valence electrons in order to become stable.